Okay, we have a What the Physics video. This one is on simple harmonic motion, also calling it good vibrations. I considered having music playing in the background. I wasn't sure if I should get the Beach Boys Good Vibrations playing, or Marky Mark and the Funky Bunch also has a version that's very different, of course. Then I realized those songs are older than you are, and unless it's by Kesha, you probably would have never heard of it before. So we'll just move on. So I don't know. I don't know who you listen to. Kids these days. Okay. I don't know. Okay. Let's see. So we did say we said simple harmonic motion, and we'll say the words oscillation. And by the way, when we say SHM, simple harmonic motion for short, okay? Oscillation, all these things, fancy way of saying something goes back and forth and back and forth. Now, there's a little bit more to it than that, simply going back and forth. Okay? Your textbook, and I'll have to read the quote because I can never remember all of it. There's a back and forth motion of an object that passes through the same positions, first moving in one direction and then in the opposite direction. Okay, and there's some type of restoring force and other things like that. And you say, okay, so simple harmonic motion is about a pendulum swinging back and forth, and maybe something on a spring, right? Sure, but don't think of it as such limited scenarios. Don't think of it as this only happens in the physics classroom. We've got plenty of different scenarios. You can be walking along and you swing your arms, you swing your legs. Those are pendulums. Okay, a boat bobbing up and down. If you have like a bowl and you have a marble, you can start the marble up on one edge and it goes up to the other edge and up and up and up, back and forth, right? Okay, so I don't know if people ever do that while you're off listening to Kesha or whatever, but yeah, that's an example. The big deal, one of the big deals I have to get through to you, is the force is not constant, and that is very, very different from what we've been seeing before. We know about Hooke's law. Remember, that was F is equal to K delta X, and there may or may not have been a negative sign in there because the force acting on the object from the spring was maybe to the right and the distance was to the left. So anyhow, the magnitude and what it shows on your equation sheet is just the absolute value of force equals K times absolute value of delta X. Point is, force varies with location, which means it's not constant. You say, well, duh. Which means acceleration is not constant. Well, duh. Okay, because F equals ma, right? Well, the not so duh part is when you realize, wait a minute, acceleration is not constant. That is going to be a problem. We've dealt with non-constant accelerations before when we dealt with uniform circular motion. Objects going around in a circle, right? The acceleration is not constant. The magnitude was constant, but because the direction kept changing, or we just kept calling it centripetal, technically the acceleration was changing, though, because the direction was changing. But it was easy enough to find a constant magnitude, right? SHM doesn't have a constant direction or a constant magnitude, which means we cannot use the big five. Just like uniform circular motion, we couldn't. But it brings us much sadness. And in case you're wondering why I have a picture of a banana, if you look at the banana, someone actually found a sad-looking banana and took a picture of it. It's awesome, but sad at the same time. So he has it. Yes, he has it split. Okay. All right. However, even though we can't use the big 5 equations, we can still use the concepts of taking the slope and taking the area under the curve. So some vague signs of happiness. Okay.
Are you hungry?
Aren't you glad I didn't have another picture of a banana, right? So it's like, hey-oh! All right. That's all I have for today, guys. No, okay. No, all right. Yay, finally I get an applause. Okay. Let's take a look at some of the pictures from the book. As we saw earlier, when we are talking about the distance, we'll see how the force will vary. So let me grab here. So right here is the cart, and the spring is not stretched. It's just in a relaxed state. Okay, so the only forces acting on the cart right now are the normal going upward and the gravitational going downwards. They are not really likely to change at this moment, so I'm going to just kind of ignore them for right now. I'm only going to focus on the forces going to the right and to the left. So, if I grab hold of this cart and I pull it over here, as is done right here, I had to do work on it. I exerted a force and such. So I did work pulling it this way. My force was to the right, and the distance was to the right, so I did positive work, and okay, so I just gave it energy, right? What type of energy did I just give it? Potential. Spring potential energy, right? Okay, and then I'm holding on to it, so its kinetic is still actually 0. So it changed for a moment, but now it's back to 0. Okay, so if I were to let go of this, so instantaneously my pulling force to the right is gone. The only force acting on it now, other than the vertical, would be the spring force. It would be pulling it this way. It would be pulling it to the left. Okay. So notice, as I said before, while the position might be to the right, if we call that positive, if you'd like, the force will be to the left, that would be negative. They're still proportional in terms of magnitude, but we do have to be careful with direction. Okay? And by the way, this is the equilibrium point, so when we have it out here, we're going to refer to that distance from the equilibrium point as the amplitude. So the greater the amplitude, the greater the force. As we look through here, actually let's go back. I release it here. What's going to happen to the cart? It's going to accelerate to the left. Okay, until it hits 0. So it will be accelerating, as in it will be speeding up to the left. Because I don't want to use the word decelerate, because that's kind of misleading to a lot of people. Okay, so it will speed up to the left. Okay, until it hits 0, and then what? Okay, at the moment it's at 0, it's at equilibrium. It'll be just like it was before in terms of force and acceleration. The force on it will be 0 because it's in its relaxed spring state. However, not just like before, what's it doing now? It has kinetic energy. It has velocity. It has inertia. It's going to keep going. Well, technically it had inertia the whole time, but you could say it has momentum. The fact that it has kinetic energy, that's the important part. It's still moving. It's not going to come to an immediate stop just like before. So what's going to happen? Well, it's going to move this way. Forever and ever? No. What's going to happen? Okay, I'll repeat that. It's going to start accelerating to the right. It's moving to the left, but it's accelerating to the right. So what does that mean about the speed? It's going to decrease. eventually it will hit some point over here and it will come to a stop. Guess how far over here relative to how far over here?
It's the same.
It'll be the same distance, right? Okay. One is, like, you can call amplitude a number of things like x and negative x or a and negative a. The point is, if this is 5 meters, this is going to be 5 meters in the other direction. Okay? And when it's over here, what type of energy does it have? No kinetic energy. What did that turn into? Yes, spring potential energy. Good. Okay? And I finally get to use this sound effect. Spring, yeah? Oh, well, that was worth it.
Totally worth the
Okay. All right, so it's going to be going the fastest when it has the greatest kinetic energy, of course. That's going to be right at the center. So what's happening at the extremes in terms of the speed? It's going to be 0, okay? And thus kinetic energy is also going to be 0. Okay? And just to make sure we understand, where are the forces? The horizontal force is going to be the largest. At the extremes, right, okay? And which way are those forces going to be pointing? You always say, I don't know, sometimes left and sometimes right. So instead we say, good, say it again, buddy. Toward the center, okay? They are restoring forces. The accelerations will also be toward the center, which hopefully that makes sense because, once again, F equals ma. Whatever the direction force is going, the net force, that's the direction the acceleration is going to be going. Okay? Good. Good. What about on a pendulum? Is that force constant as well? You say, well, no. And we've already dealt with pendulum before. So we know that the force is not constant. Okay? Say, Pharaoh, when did we deal with the pendulum? I remember that at the beginning of the year, but we didn't talk about forces at the beginning of the year. We've talked a number of different times about the kid at the swimming hole, right? The kid is on some like ledge or cliff or something like that, and he's got some rope, like imagine like a tire swing, and he swings down toward the water, and he's going in an arc. We talked about that in terms of circular motion. We talked about that in terms of energy conservation. Remember we said the work being done by the tension is 0 because they're perpendicular. It's perpendicular to the distance, right? That's kind of a weird one. And then now we're talking about it again in terms of simple harmonic motion. Of course, it kind of implies the kid would just keep swinging back and forth, but same basic premise. Okay? What I'd like you to do is take a moment and draw out the forces on there. We already know that there's going to be tension and there's going to be gravitational force. Are they going to be the same the entire time? Are they going to be the same magnitude but different direction? I don't know. Well, I do, but I'm wanting you to do it. Okay? Fill that in, please. Okay, once we've got that, and hopefully we realize that gravitational force is not going to change, it's always pointing downwards, and as long as the mass and the gravitational field are not changing, it's going to be the same size. The tension will be varying, of course, in direction and in magnitude. Okay, and while we're at it, if you've already done that, go ahead and draw it out for these guys. Should be pretty easy based on what we've just been talking about. This isn't an official free body diagram, so I don't need you to worry about the verticals. Okay, just focus on the restoring force, please. Try to keep a reasonable size magnitude, relatively speaking. Okay, so hopefully people have drawn in. What have we got is the direction of the force over here to the left, and is it big or small? It's going to be relatively big, as opposed to over here. How is this one going to be different? And how is it going to be the same? Same magnitude, but opposite direction. Excellent. How is number 2 going to be different? Or maybe it's not different. Okay, well, this dotted line here is supposed to suggest that's the equilibrium point. Okay, so that's okay. That's why I'm discussing it. Okay, so I didn't say, hey, by the way, this dotted line. Okay, so I'm saying that now. Even if you hadn't realized that, you know it would have been a lot smaller if you did try to draw on a force right here. But right here, the force, the horizontal force, is going to be 0. Okay?
The net horizontal force or any horizontal?
Well, the net or any, I'm sorry?
Because you could have 0, the force could be 0, but you could have force going in both directions.
Okay.
And that would still make...
We're only talking about a restoring force here from the spring.
Okay.
There's no frictional force, and we wouldn't have the spring exerting that one spring exerting a force in 2 different directions.
Okay, so it would just be 0. Okay.
Right.
Okay.
Yes.
Just making sure I get that.
Good. Okay. All right, and in case you're a scrub and you didn't get it very well in the first place, physics classroom already drew this in for us. Okay. Good old physics classroom. And they also did it here. So, yay. Okay. Now, their drawing, I like this one a little bit better because, as we were just talking about the general size, this one, when it's stretched out the most, to the right at least, it's nice and big arrow. This one is a smaller arrow, then it's to 0. And then a smaller arrow to the right, a bigger arrow to the right, and so on. Okay? Say again?
On the very right-hand side of the screen, there's 2 air supply.
Okay, all right. 2 air supply. Anyone?
I think there are like holes in the
Yes. If you would actually, if you look at physicsclassroom.com, like I said, this is just an image from there. They would have explained that this is on what's called an air track, and air track is, if you've ever played air hockey before, okay, so it's little, well, air is coming out of these tiny little holes, thus effectively making 0, well, negligible, we'll say negligible, okay? There's still going to be, of course, a tiny amount of air resistance, friction, and I guess air resistance too, but it's practically 0. Okay, so if we had those things instead of the low friction tracks and carts that we have, it would be even better, but they're difficult to set up and they're expensive and stuff. So, all right, so back to the pictures from the books. We have a situation where the cart is stretched over here, but we release it and it just goes back and forth, back and forth. Okay, here's dot diagrams for acceleration and velocity, and then for force right below. Okay. I'd like you to look at this in terms of what types of relationships do we see. So take a moment and say, okay, right here the amplitude is at its maximum value. Okay, so is blah blah. So is da da da. Okay, and then as the amplitude increases, so does so on and so on. Okay, and that's actually a slightly different wording than from this one. Okay, and when the amplitude is at its maximum, what is not at its maximum? Okay, so take a moment, fill in, and then check with your neighbor. Okay, so what did we figure out? When the amplitude is at its maximum, what else is at its maximum? Say again? Acceleration is also at its maximum. Anything else also at its maximum? Force is also at its maximum. Okay, anything else? Spring potential energy. I didn't talk about the bar charts down here, but you should definitely be able to interpret them. Yeah, spring potential energy. Because after all, where's that force coming from, right? It's a spring force. Cool. Good stuff. All right. As the amplitude increases, so does, okay, and anyone guessing at what I was talking about in terms of how is this different from the previous question? Okay. Right, so as I get further away from zero, that's what we're talking about by amplitude. So amplitude is our generic location, okay, from this reference point. And I'd say, all right, this way is positive, this way is negative, right? Okay, so amplitude is increasing, that means our distance is increasing, but that's the same idea, that's how we define it, right? Okay, yes?
The potential energy increases exponentially.
The potential energy is also increasing, and there's, you mentioned exponentially, that's because of...
the square in the equation.
Right, okay, so if we recall the equation for spring potential energy, that's 1/2 times K times delta X squared. So yes, true, okay? What I was trying to get at too was, even though amplitude and force might be at their maximas at the same time, you do have to be careful in what you're saying and how you're wording and stuff like that about, oh, as the amplitude is greatest, so is the force. If we're talking about the magnitudes, yes. Okay? Because you could make an argument one way or another. Well, amplitude is largest positive value when the force is its largest negative value. Okay? So that might throw some people off. Okay? I don't want to say it's the minimum, though, because in that case, the force is... Well, actually, let's move on to the next topic. Okay? So, we just said about that. When the amplitude is at its maximum, what is not at its maximum? What did we say? Okay, and why is that? What do we think? We said it before, and we're summarizing. Okay. Ooh. Okay. Right. For that split second, it's not moving. And this is what we saw on our spring oscillation. So it counts for a horizontal spring in this case, as well as the vertical spring that we saw in the simulation, going up and down. Also, my trusty setup right here, which of course the 5 people that are listening to this recording can't see, but it's a hanging spring just like we had in the beginning of the year, okay? And it's going up and down. Now, it's a lot easier to deal with a horizontal oscillation than a vertical, because, well, actually, why?
Because there's a force of gravity that you have to take into account.
Right, force of gravity, and that also means there's
Acceleration due to gravity?
well, acceleration due to gravity. Right, I was going for the potential energy for gravity. Right, okay. But one of the cool things on that simulation was, and hopefully you saw it, you can actually graph out the different types of energy in the bar chart going up and down. Okay, so what we're seeing here, and my spring is still oscillating, if I make the spring come to a stop, right here is my equilibrium point. Okay, on the screen, so back to those people that are watching this at home, on the screen that would be like right here. And I said at that moment, the spring force is 0. Is the spring force 0 here on my hands-on one? No. So that's a little bit weird. Okay? It's in equilibrium, but I can't say that my spring force is 0. Where would a spring force be 0 on a oscillating spring? I'm sorry, vertically oscillating spring.
Stop.
Yes, at the top. So this is one of those weird things. The horizontal, I don't have one of these springs that you can stretch and you can compress. Most springs that you've ever seen are just going to do one or the other. Okay? Even a slinky is a spring that you can stretch. What about when you try to compress a slinky? Does it do much of anything? No, it just sits there, right? Okay? So that's the problem. So unfortunately, I don't have any tangible guys for the horizontals. Okay? But yes, as we had mentioned, so let's move on to the... Oops. Oop, too far. Okay? So yeah, the velocity and the kinetic energy are going to be at low points when the amplitude is at its maximum. Okay? Good, good. Questions? Right. So the restoring force, as we had just gone through, has a maximum spring potential energy when the amplitude is maximum. Okay? The restoring force is always trying to take you home, is my wording, not a textbook's wording. But it's trying to bring you back to the equilibrium point. Okay? But the problem is, where the force is 0, the velocity is at its largest, so it's going to overshoot it each time. It's just going to keep oscillating back and forth. And we saw that with the free body slides and such. To make sure we understand the concepts here, try this out. And this comes from your textbook. So perhaps you've already looked at it. Brian places a book on a desk and pushes it right to left on the desk. He says the book undergoes vibrational motion. Explain what features of the motion might make Brian say this. Then explain why this motion does not fit our definition of vibrational motion. So the idea is, part of what he's thinking is correct, but part of it is incorrect. So I want you to identify what is correct and what is not correct. Okay? And explain. Okay, so let's go ahead and check these. All right, so, and folks, this is an important skill to be able to, to have and be able to demonstrate on not just my test, but also the AP exam itself, right? You have got to be able to not only recognize physics and work through problems and number crunching and stuff and demonstrate with diagrams, but you've also got to be able to make an argument that is logical and physics-based, and I'm not going to say attack and tear down someone's argument that is not physics-based, but you have to be able to point out the flaws in their understanding. And these might be flaws in your understanding too, so it's helpful for us to point these out and say, oh, see, I thought it was like this, but what you're saying is it's not. Okay. And then hopefully that'll help. Okay? So, as we said, explain why Brian thinks it is vibrational motion. Yes?
Because it's moving in the same pattern.
It's moving in the same pattern. You mean it's moving back and forth, right?
Yeah.
Okay.
It slows down as it gets to the extremes.
Okay. Well, it didn't specifically say about slowing down when it gets to the extremes. You could argue one way or another. Is there friction? Is there not? Nothing was mentioned. So your visualization might have friction. And then, yes, it would slow down. Or, if it didn't have friction, I mean, it's going to slow down at some point. Why? Yeah, because your other hand is going to push it back the other way, right? Okay, sure. So, yeah, that makes a pretty reasonable argument for vibrational motion. Anyone else want to toss in on that? Yes?
He's right in the fact that when the book is moving from when it's at its max distance,
Mm-hmm.
that is where the maximum amount of force is going. That's where when it's at that max distance, the same no matter what it is, it's the same magnitude of force that he's applying to it each time. And it's
Okay, so in terms of springs, you're pointing out that the largest spring force is at the very extremes, right?
Yes.
And in terms of Brian pushing on the book,
Mhm.
the largest force is going to be at the very extreme, right? Okay. But is his force beyond that? Is his hand force behaving like a spring?
No,
Okay. Why? What is wrong?
there's no equilibrium.
Okay. There's no equilibrium point. Okay. Good. And remember, we said the whole idea of the restoring force is it's trying to bring you home. Okay. All right. What else?
If there's actually springs, there would be a force pushing it at every moment except for when it's at equilibrium.
Right. So there's a force pushing or pulling on it the whole time. Okay. And it's always a force trying to get us back to this equilibrium point, which this book does not have.
Because if you have it going like this, then there's only 2 incidents for this force.
Right. So if he only pushes on it at the very extremes, then there's only those 2 extremes, only those moments that it's got the forces pushing on it. Okay? And those are the largest forces, but they're the only forces. Okay? And if you try to argue about, oh, but I had the friction in there. Okay, but is that always pointing toward if we imagine the center is the equilibrium point, is that always pointing toward the center? No. Okay. So, makes sense because of it's going back and forth. That's vibrational motion. But then when we look into it a little bit deeper, we're like, oh, well, I guess it's not actually vibrational motion. Okay? So you driving a car back and forth from your house to school is not vibrational motion. Okay? You being on a swing set, well, that's something else. Okay, as in, that is not the same as driving a car back and forth. Now we might be talking about vibrational motion.
Would you say engine is vibrational motion?
An engine is vibrational motion.
The air and then it blows up.
I'm sorry?
Well, I was thinking about like an engine where you have pistons,
Mm.
it compresses the air and then it explodes and pushes it back up. But the problem is it's not pushing itself back down. There's not a piston pushing it back down.
Well, I don't actually know a whole lot about engines other than very basic,
And it's fluid.
very basic stuff about like pistons and such like that. So I wouldn't really be able to say, is that truly vibrational or not? So, sorry. Okay. Sounds coming from the engine, though. Certainly, yes. And we'll actually be talking about vibrations as sounds soon, but not immediately. Okay? Let's talk about some vocabulary. Okay? We're finally getting around to defining frequency and period. Say, yeah, well, it's about time.
Yeah. Oh my.
Oh,
Yeah.
no, I'll do this one instead. There we go. That's pretty much. All right. So actually, as I said, we actually already defined them back when we were discussing circular motion. So, but just like in vibrational motion, here we go again. Really? Here we go. Again, it's.
Come on.
That was so bad.
Okay, so period, which is capital T, is how long it takes one complete vibration to go back and forth. Now we're talking about amplitudes, positive A, negative A, or positive X, negative X, or whatever. Okay? We would typically discuss these in terms of seconds, although we don't actually have to. Could be years or months or whatever. But if we're going to do a calculation, we should use standard units, which is seconds. Okay? Frequency, we already talked about lowercase f. That is very closely related to period. In fact, it's the inverse of period. It's the number of oscillations or vibrations or wiggles per second, or per any time interval, but like we said, our standard is going to be per second. Okay, instead of saying vibrations per second, we can simplify it down to hertz. Say again?
That hurts a lot.
It hurts a lot, right? Yeah. It's a. If someone ever asks you for if you want to try a Hertz donut. Yeah. Don't fall for that. Okay. Yes, sir.
Are there any things that have like an amplitude that take a year?
Things that take a year.
Like that are vibrational motion that take like a month or a year?
Well, is there anything that has a period of a month or a year?
Period. The Earth has a period of the year. It's not
Okay.
vibrational.
Well, okay. Arguing the whole vibrational thing or not, we can simply, I don't know if you're going for specifically, is it simple harmonic motion or not, but Earth has a revolutionary period of a year. Now, in terms of, it's not vibrating around in a year, okay? There's no restoring force and such like that. But is that what you meant, or?
I meant kind of like, is there something like kind of like a pendulum that takes like a month to swing back and forth?
Wow. Okay. Well, let's.
Like a pendulum, because a pendulum, even if it's pretty big, it still takes like 4%.
Okay. From what we know earlier. Well, actually, I'll ask you from what we know earlier. What would make the period of a pendulum longer? Would I have to have a short length of string or a long length of string? I want a long length of string. Okay. And actually, we'll see the relationship later on in our notes. Okay. But in order for it to be a month, I don't imagine that actually happening on Earth. Okay. We could. Yeah, I just don't see that happening. Okay, that'd be an impressive pendulum. Okay. We already mentioned you're able to go back and forth between period and frequency just by inverting. This guy, we've also mentioned, but I don't think I've actually used its Greek letter before. It's angular frequency, which is showing up here. It looks kind of like a curvy W, but we call it omega. Okay. That's when you'd say frequency times 2 pi. Or you can say 2 pi divided by period, whichever. Okay. If you recall earlier on in the year when we were doing circular motion, and I was talking about the physics slap. So I have my arm extended, for the 5 people listening at home. I have my arm extended out from my right side. Okay, it's my arm is straight out. And if I swing it forward, so it's now right in front of me.
Pardon this interruption, General.
Physics. Okay, real quick. As my arm swings around, if I were talking about the tangential speed of various points on my arm, like my elbow, my thumb, and my fingertips, they would all have different tangential speeds, but they would all have the same angular speed or angular frequency, right?
Yeah.
It doesn't matter about the radius. We will talk more about that when we get into rotational motion. That will be our final unit, okay? But I figured it would be worthwhile talking about right here because we will discuss it. And you can practice these example problems, and then we'll go over it later on. Okay? Delicious.